Welcome to session 7 in the series Unlock Circuit Design using ADS. And I'm of the opinion that there are three things which are required to learn any subject. One is sufficient amount of practice. Two is the theoretical background. And three is the visualization. So if you have a lot of practice but you don't have theory, then you will be having a lot of thumb rules which are not good, right? And if you have a lot of theory but you don't practice, then you cannot be productive. And if you do not have visualization or imagination, then you would not be able to design new circuits. You will be only doing bookish circuits, right? So all these three are important, right, to design a circuit. So I'm going to do a little bit of practice and a little bit of theory. So let me make a new folder here and call this as gain stages. Gain stages, correct? And then in this gain stages folder, I'm going to talk about three uh, three amplifiers. So one would be common source. Okay, so let's create a common source amplifier. Okay, so now let me try to explain you how this common source works, because now we have a small signal model, right? So we should be able to see what a common source is. Now before I even approach this, let me figure out what is a small signal model for a current mirror. So if I say small signal model for a simple current mirror, right? Current mirror. Okay, so that's what I want to do. Okay, so now the first and foremost is there is a circuit in which I have a transistor which kind of looks like this, right? And it is drain is shorted to the source. This is referred to as diode connected transistor, right? Now let's see what is the property of this. So if I assume a very simple model like this, right, then what do I have? I have the gate, and then I have a certain voltage as the input voltage, right? And then I have this, right, that is GM, and I have shorted the gate to the drain, and then this is grounded, right? Same is the situation if I reverse it also. So if I reverse it, this would look like this, right? So this is the source. In this case, this is the source, this is the drain, this is the gate, and this is the gate, and this is the drain. So when I do that, okay, it's just a question of polarity between NMOS and PMOS, so it really doesn't matter. So when I do this, I know that the voltage across drain source is going to be VI, and the current through it will be GM VI. So the resistance, output resistance, is equal to 1 over GM, right? Now in this case, I have ignored this. So if I have this, which is GDS, okay, so that would be basically 1 over GM plus GDS, or rather you can say GM 1 over GM in parallel with RDS. I did a mistake here, sorry. Okay, so this is parallel combination, so it will not be like this. 1 over GM is the resistance. Okay, so let me do this. So right now we have a parallel combination, right? So the net resistance would be GM. So it will be conductance will be GM plus this conductance would be 1 over, am I right? So this is the resistance, right? 1 over GM. So conductance is GM, and this is GDS. So GM GDS should go in parallel, isn't it? So 1 over GM is in parallel with, sorry, so 1 over GM is in parallel with RDS. Okay, so that is the RO. And if RDS is much larger, then what you are left with is equivalent resistance is equal to 1 over GM. Okay, now One more thing you have to consider when you do circuit analysis is that for small signal or AC, okay, for AC, DC voltage source, DC voltage, sorry, voltage source is 0 volts, and current source, DC current source, right, is open. Okay, so this is all you have to remember. DC current source is going to be open, okay, or infinity, okay, and DC voltage source will be shorted. Now what's going to happen is, if I draw the entire current mirror, okay, so that can be replaced as 1 over GM, but the voltage over here is going to be 0 volts, because this is a DC voltage which is biasing another. So if I look at the current mirror, right, it is going to be biasing another transistor here, plus minus, and there is a GM again. So let's say this is GM1, this is GM2, and then this is going to be GDS2, and I am trying to find out what is the output resistance of this. So I will put a small signal over here called Vx, which will force a current Ix. Now this net voltage over here is 0, that's why GM2 into 0, so the net current drawn here would be 0, right? So all the current which I force into the output will go through GDS2. That means that the output resistance RO would be equal to RDS2, right? So if I take a current mirror, right, so whether a NMOS or a PMOS doesn't matter, one part of this is going to be a diode connected transistor, and you will pull out certain current IRAF, okay, and let's say that this is going to be 1:10 ratio. So we have seen what is a current mirror, right? So this is a 1:10 ratio, 1:10 ratio, right? Now this one has an output resistance of RDS2, correct? And then there is going to be a gain stage here, okay, where here I will put VI on top of a certain bias, so this will be VB. So I'll put a VI on top of certain bias, and then I'm going to tap in output voltage over here, right? So now in this case, what's going to happen for this transistor, the second transistor, which is going to be, this is T1, this is T2, and this is T3. So for T3, let's say the output resistance is RDS3. So now let's me draw an input model for this. Now I can consider VI over here, plus minus. This is the gate input. Forget about the DC bias, it is 0 volts for AC analysis. And then I have GM3 over here, and then I have GDS, so this is grounded. I have here GDS3, and then there is a GDS2, right, and that is to ground. So remember I told you the DC voltage is considered a small signal ground, so this is going to be a small signal ground, so that means that this is in parallel with that. Okay, so now if this is the scenario, now let's say that this is VO, right? So this VO times of all the, so I'm going to apply Kirchhoff's current law here. Okay, current law would be VO into GDS2 plus GDS3, because they are in parallel, right? GDS2 plus GDS3 would be the total this, and then the current flowing out of it is going to be positive. So all current flowing are taken as negative, or current flowing out are taken as positive. That will be equal to GM3 times of VI, and that would be equal to 0. The net current flowing out of the node is 0. So that means VO GDS2 plus GDS3 is equal to minus GM3 times of VI. So VO over VI is going to be AV, or the voltage gain, which will be equal to minus GM divided GM3 divided by GDS2 plus GDS3. Okay, so this is going to be my current gain. What about the voltage? This is going to be my voltage gain. What about the current gain? the net current flowing into the gate is 0. Okay, and the current flowing into the drain is some value. So some value divided by 0 is going to be infinity. So for a small signal, for low frequencies, I can assume that the output impedance is the current gain at low frequencies is infinity. Now let's look at what is RO. So to find out RO, what you have to do is you reduce all the voltage sources to 0 other than the one which you are going to investigate, and then you also replace the DC voltages by short and DC current sources by open. So if I do that, what is going to happen is this is short and this is short, so basically net voltage here is 0, right? That's a small signal voltage. Then this voltage, this current will be GM0, that will be no current would be drawn in this branch. And then what you have here is GDS2, and then you have got GDS3, and then what you do is you attach here a small signal voltage Vx, which drives in a current Ix. Now the Ix is only flowing through these two combinations, not through here. So if I was to write the equation, the Kirchhoff's current equation, Vx will be equal to, Vx into Vx multiplied by GDS2 plus GDS3. Okay, so the current flowing out is positive and current flowing in is negative. Minus Ix is equal to 0. The net current flowing in here is anyway 0 because the input voltage is 0, right? So that makes Vx by Ix is equal to RO, which will be equal to 1 over GDS2 plus GDS3. Okay, so this would be the output resistance. Okay, the next thing which you want to know is what is Ri. Ri is going to be Vi by Ii. Now if this Ii tends to 0, then this value should be equal to infinity. So let me sum it up. Okay, sum it up this way. Now I'll tell you for common source, and I'll tell you why it is called common source. For common source, and the reason this is called common source is because the source is common between output and input. Okay, source is a common ground between output and input. So voltages are with respect to source, which is common between input and output. That's why it is called common source. So for a common source, okay, AV is equal to minus GM3 times of okay, so just 1 second. AV is equal to this thing divided by GDS2 plus GDS3. That is AV. Okay, or it can also be written as minus GM3 times of RDS2 in parallel with RDS3. Okay, so what does it mean? It means that the voltage gain will go up if the GM goes up, right? Now, if the GM goes up, RDSs will go down, because if you see, to take the GM up, you have to, so GM is basically twice of IDS by V overdrive. Okay, so if you take GM up by increasing IDS, then what's going to happen is the RDS is going to go down, as we have discussed earlier, right? So that's the issue. Now, V overdrive can be fixed with the size of a transistor. Okay, so if we have a smaller V overdrive, okay, that's for a given current. If you have a smaller V overdrive for a given current, so what does it mean? The device has to have a very large W by L. Okay, that would push the GM up. Okay, but then if you want to increase W by L and take GM up, so you should do so what you should do is you should take L also up. Okay, and then W also up, then you will get the output the voltage gain to be high. If you just increase W by L, current would go up, or rather if I have fixed the current in overdrive, we are changing, right? So that means that the bias voltage we are changing on the input. Okay, then that way also we can, but then we are restricted on the bias voltage. VGS minus VT is equal to V overdrive. So VGS, okay, so we have V overdrive is equal to VGS minus VT, and then the bias point VGS would be equal to VT plus V overdrive. Okay, so we take the input bias up and a larger transistor, you'll be having a higher GM, right? So that's one way. Other way is you increase L, okay, and keep WL constant by increasing W by same amount. That will increase RDS2 and RDS3, and that will increase the current, the voltage gain. Or you reduce current, so you will be bringing down GM, but then you will be increasing RDS2 and RDS3. Okay, so that is AV. AI is equal to infinity, RI is equal to infinity, and then you have got RO is equal to 1 over GDS2 plus GDS3. Okay, that's what we derive, right? Yeah. So this is a common source amplifier. Now there are other ways of taking the RDS up. We have already discussed in case of a current mirror, and we will derive it. So for now I have a current mirror here, a simple current mirror, which we did in previous session. Oh, this is a cascode. So let's just pick up one of them. This is 2:20 ratio. Edit copy and then edit paste. Okay. Okay. Now what I'm going to do is, this is a current mirror, so I have a diode connected transistor over here. Okay. Now I can force any current over here. I can get 10 times the current over here. Now we will see trade-offs, and then we can do it exactly. So let's put here a voltage source. Okay, so that voltage source is 2.4 volts, for example. 2.4 volts. 2.4 volts. Correct? And what you do here is put a current reference. So okay, so this I'm going to keep this current reference to be 100 microamperes, and I'll tell you what happens. There are lots of trade-offs involved here. 100 microamperes, so I'm expecting 1 milliamp on this side, and then I need an NMOS, so I'll just say copy this one, flip this one, place it here, and change this to N, and then use and can change the model to NFET4. And then I will display only what I want. Okay, so I'll just display this, and then I'll display multiplicity. Apply. Okay, so if I want F5 for the text, so I'll come to this one. Okay, so now this is what I'm going to do is I'm going to do this as 1/3 the size. So 1/3 of 20 would be like 7 here or 8 here. Let's put here 8 here. Correct? Now I have to first I have to find out what should be the bias. The bias would be V overdrive plus VT. The question is, what is V overdrive, right? The V overdrive you can compute with the current. Actually, we have current and the size, we know the V overdrive, but this is like an analysis. Okay, synthesis is the reverse of that problem. So let's first do an analysis and then I'll tell you the synthesis part. Okay, so I am going to put here a DC voltage, sources frequency domain DC, and I'm going to sweep this from 0 to 2.4 volts, correct? So I'm going to take this and I'm going to sweep this one, so this I will call as VI, and then this node voltage I will call VO. Sorry, so I'm going to name this node as VO. Okay, so I want to plot VI versus VO when I'm sweeping it, so I'm going to do a DC analysis on this. So that's the DC analysis, and here I am going to sweep VI from 0 to 2.4 volts, which is the supply, to 2.4 volts. Okay, in steps of very small steps, 0.001. Okay, fine. So, and then I have to declare a variable VI. Okay, so there is a variable VI. So the default value can be anything because I'm going to sweep it, and here I'm going to sweep VI, so I'm going to display this at the output. Okay, so this is my sweep and I'm plotting wave. One more thing I need in this is the include file. That's my include file here. Okay, so this I'm talking about is common source. Okay, so let me just do a simulate on this. I think everything looks okay, right? Okay, so I'm plotting static characteristics of this amplifier. Okay, okay, so the static characteristics of amplifier is going to look like this. What happened here? 100 microamperes, VI 0 2.4 volts. Oh, why it is 1? It should be 0. Okay, 0. Okay, simulate this again. Okay, so now you see that there is a gain. The slope is the gain, but the gain is negative, right? So that's what a common source amplifier would do, a negative gain. And I'll come to what that negative gain is. Okay, so I'll put a marker here. Okay, and then this is more or less like an inverter, right? New marker over here. Okay, so the gain of the circuit would be given by, another thing is I will put one marker at the center. The center happens at 2.4, so 1.2 volts. So at the center of the transition I am at 1.2 volts. So that means that the input is 0.537. Okay, so okay, let's find out what is the gain. So equation gain, so gain in pure number. So this gain in pure number would be equal to m2 minus m1 something divided by something, right? So it will be m2 minus m1, right, divided by independent of m2 minus independent of m1, INDEP. Okay, so this is the gain. Okay, gain would be a negative number. Let's see that negative number. So if you go to equations, you will see gain. Okay, so gain is minus 12, correct, or minus 13. Now this minus 13 is the gain as a pure number. So let's express this in dB, right? So this would be gain in dB, right? And I forget about the sign. If I say the phase shift is 180 degrees, so I will put here a minus sign here, and then I would do a 20 log of this. Okay, so it will be 20 times log 10 of this number. Okay, 20 times log 10 of this number. Okay, so this would be the gain. So let me put here gain in dB, Control C, Control V. Okay, and here I have to just put here dB, change the name. Okay, so 22 dB is the gain. Okay, now the question is, this is called analysis. Okay, now one more thing is there. If I want to improve the gain, what do? I can change the length from 130 to 260. So everywhere I'm going to do 260, right? So everywhere I'm going to do 260, 260, 260. So I'm not disturbing the ratio. So still, what is going to happen is the gain is going to go up by changing the length. So if I do that, okay, so I have to readjust these. So 3 is around 1.2. Okay, roughly over here, and let's bring this over here. Okay, so the gain has become 28 dB or minus 25. So now you see that increasing the L has increased the RDS, and as the RDS goes up, the gain goes up, right? So this is one way of improving gain, is by doing that. Now what happened to the current? The current has remained the same, but what happened to W by L? W by L is reduced. So when W by L is reduced, V overdrive has gone up. So the net swing, okay, so you are going to lose V overdrive over here, and you are going to lose V overdrive over here. So the net swing would be only this much. Okay, so let me just tell you what's happening here. Okay, so this is the net swing, and this one is V overdrive. So at the top you lost V overdrive because that voltage would cause the PMOS device to go into triode region. Right, and this voltage will cause the NMOS device to go into the triode region. So you will lose all the gain because the RDS has gone. So basically your useful gain is only between, so it is only between VDD minus V overdrive and V overdrive. So your range is from V overdrive to VDD minus V overdrive. So it will be VDD minus V overdrive. Correct? So this is your useful range. It's not a minus sign. So let me write down here text 2. Okay, so your swing is this. Okay, so you understood that if I reduce W by L, okay, then my overdrive will go up, and this swing will go down. So this is the price I have paid for improving the gain. Another price I have paid. The other price I have paid is that the input voltage range VI, which will be basically independent of M2 minus independent of M1. Okay, so the range, input range. So let me just take this value. Control C, and I would say equation. I'll call this as range vi will be equal to this, correct? And let me put here range vi. Control C, Control V. Range vi, sorry. So range vi is only 60 millivolts. So your bias point is around M3, which is 0.612. So you can go 30 millivolts on the left and 30 millivolts on the right. So your input voltage range has shrunk because the gain has gone up, sorry. So if this is the scenario and you bias the part at 0.612 and suddenly there is let's say temperature variation, VT changes. So if VT changes, then this transistor will no longer show you gain because it might fall out of the maximum gain region, which is 60 millivolts. So 60 millivolts of input is too small, around 0.612. If you have a slight change in VT because of temperature, you will be going out of this range, right? So that's a problem, right? The input voltage range is too little. And the first problem is that the V overdrive is basically limiting Marsh swing here. That's why we had a wide swing cascode, right? Because we want to have a wide swing across the output. That's why it is called wide swing cascode, right? So that's the whole idea here. Okay, so I think you have learned a lot on the common source amplifier. Now let's just look at the synthesis part of it. So how it will start? It will start with the following. Okay, somebody gives you a power dissipation. Somebody gives you a power dissipation, and let's say that this power dissipation is, let's say, 1 milliwatt. Okay, next thing is they have told you what is the swing, output swing. So first thing they have to give you this, second thing they have to tell you what is the output swing. Sorry. So then they may say, okay, the output swing is going to be from a 2 point, so they will also give you VDD. Okay, so second thing they will give you is VDD. Okay, let me just change this. Okay, second thing they have given you is VDD. Third thing they have said that the swing is 80% of VDD. That means that they have told you what is overdrive. So they have told you from here you got from here you got 80% of VDD, so you got your this, and from here power dissipation, from power dissipation you got your currents ID or ICQ. Okay, you got your current here ICQ. Okay, so you got your V overdrive. So V overdrive would be equal to square root of current twice of ICQ mu n cox W by L. Okay, so they have given you V overdrive, they have given you ICQ. From the process you know what is cox and mu n, then you have only this unknown, so you know what is W by L. So from this you got W by L. So once you have W by L, then you say you want a gain. Okay, let's say you want a gain of 30 dB. So in pure numbers it will be a gain somewhere around 27, 28, roughly like that, right? So once you have the gain in pure number, you will say that the gain is GMRO. So GM is twice of ICQ divided by V overdrive. So this is GM. RO is going to be GDS2 in parallel with GDS3. So let's say two GDSs are same. Okay, so it will be uh, RDS2 in parallel with RDS3, that will be RDS by 2. Okay, so RDS by 2. So from here you got the gain ICQ overdrive, so the only value is RDS. So once you know RDS, you know that RDS is equal to twice of, in this case, IC. So let me just write it, twice of 1 over lambda times of ICQ phi 0 divided by 1 plus phi 0 by VDS minus V overdrive. Okay, so we are looking at the center, so which will be VDD by 2 minus V overdrive, which will be known, plus phi 0. Okay, so from the process you will have this, you have then VDD is given to you, V overdrive you have found out, then RDS is given to you, then ICQ is given to you, so you got lambda. Lambda is equal to KDS divided by twice of L of root of VDS minus V overdrive plus phi 0. Again, okay, KDS is equal to root of twice of epsilon over QNA. So from a process point you have KDS. Now you have got lambda from that equation, right? So now what you have is L. So you have figured out what is L. So you know what is W by L, and you also know what is L. So this gives you W. So once you get W by L for a gain stage, so this will be W by L3. Now, okay, you want to keep the bias point. Okay, so now what you want to do is, okay, so what's going to happen is, this is for 3. So W by L for 2 would be almost, so what is that? So if the mobility is like 1/3 for a transistor, PMOS transistor, so it will be 3 times of W by L3, correct? So now you have that second transistor figured out, and you choose the L to be the same, L3 should be same as L2, so you will have W3 and W2 figured out. So now you have to figure out W by L1, which will be basically just from the current, and you can basically start with VDD is equal to, so if I consider 10% current, right, so 1.1 times, so 1.1 times of ICQ, right, 1.1 times of ICQ into this will be equal to the power dissipation, right, that's given at the top, right? So that's how you figured out ICQ. So that means that this is going to be 1/10 of W by L2. So now this is a problem which is called synthesis. So you have synthesized for a given gain and given swing and given power dissipation, you have figured out W1, W2, W3, and then you have also figured L1, L2, L3, and from this you have also find out the bias point is V overdrive 3, which is same as V overdrive plus VT. So this is going to be your bias point, right? So you have figured out everything. You have figured out the design, you have figured out the bias. So this is how you basically do a synthesis problem. Okay, so it's like what designers do is trial and error. What I did at the start. Okay, what did I do at the start? I just did this trial and error, and I got the 25 dB gain. I can start the other way. I can start with power dissipation and swing and a gain, and then achieve the sizes. So both is possible. You can write a MATLAB routine to do synthesis. Just give it a gain and swing, and you will be done with, and the gain and swing and power, and you'll be done with this. So one is analysis, other is synthesis. Now what happens with the designer is, after certain years of experience, They say, oh, I don't want to do all this maths, right? Who will do all this maths, right? As long as you have your insight clear, you don't need maths. But if at the start itself I say you don't need maths, then you will be on the wrong path of designing. Okay, I don't want you to be on the wrong path of designing. Okay, so the way I do is, when I started as a designer, I wrote a MATLAB routine for getting a certain gain, a certain for a certain power dissipation. I wrote that. Now when the intuition is clear, my intuitions are clear now, so I know that I can design this very quickly. Okay, so this is a common source amplifier. Now what we have done here is just what you call the DC analysis. Okay, so what I want to do here is the AC analysis of the same amplifier, right? So I know the bias point over here is 0.612, right? So I will just go ahead and quickly do that. Okay, now let me tell you one more thing. There are lots of simulators, and I ask this question again and again to people. Where do you use AC simulation? Okay, and most of them can't answer this. Okay, the thing is, what is AC simulation? AC simulation basically takes a non-linear device, like these transistors are non-linear. Out of a range they are non-linear, and linearizes them. So if I put a VI, okay, of 0.612 here and put a signal on it, okay, then a very small signal, because it's a 30 dB gain, so VO will be 1000 times of VI. So if I was to do VI as a few millivolts, then let's say 1 millivolt and 1000 gain, so 1 volt swing would be over here on the output, and that 1 volt swing, if I exceed, then this 2.4 will not be sufficient, right, to achieve swing. So it will be a non-linear response here. Now what AC simulation does is it linearizes these devices irrespective of the supply. And once you linearize, even if you give a 1 volt input, okay, the output will be 1000 volts irrespective of what the supply is. So the circuit has been linearized, that's why it is giving a 1000 volt output. So what if the input is 1 volt, the output is going to be the gain. Okay, so if input is 1 volt, the output is going to be gain, right? And you need a AC simulator to do that, because you for a non-linear simulator it will not cross 2.4 volts, right? So linearizing the components around their bias points and then simulating it. And what is the whole goal of AC simulation is to figure out the stability. So the next exercise which I'm going to do right now is to figure out the stability of this common source, and then I will stabilize it, and later I will derive why it got stabilized. Okay, so I will go here, file, and say save as. So I'm going to save this design as CS underscore AC underscore AC. Okay, so once I have saved this, it has changed the name over here. What I will do is I will throw this out. So I'll just delete this one. So that's a delete. And here I just don't want this one also, so I'll delete that. This one I will set to 0.612, okay, because that's what the bias was. Okay, the bias has become 0.612. okay, so this is from the static response. And then I will put here AC source frequency domain VAC. That VAC I'll put here. Okay, and then in this VAC I'm going to have a 1 volt input, so the output would be the gain, and frequency is going to be swapped, but then I am going to add VDC to be VI or V bias, right? And I will display that at the output. So I can put a voltage here also, doesn't matter. Okay, so let me just display this one, VDC, display to the output. Yeah, so this is over here, VDC. So I am having Vi as the DC voltage, and then I am swinging 1 volt at the input. Because it's a AC simulation, it's okay. So output can be around 1000 volts, right? Irrespective of supply. Then I will be able to get the gain. Okay. So now I'm going to do here AC analysis, simulation AC. Okay. So when I do simulation AC over here, I can go from 0, or not 0, 1 hertz. Let's say 1 hertz to 10 gigahertz, and I will do a log, and I want 80 points per decade. Okay, so I'm doing 80 points per decade. I'm going from 1 hertz to 10 gigahertz, and I'm going to say okay. So don't worry about this, or if you want you can correct this. You don't have a step here. Okay, 80 points per decade. So now I'm going to hit the simulate button, and then I'm going to plot VO in dB. So that would be the gain, and then I will do is I will put the axis to be a log axis. Okay, so now what you see here is a familiar Bode plot. Okay, so this is your near to 30. So we figured out from our equation it was 25.26 dB gain. It turns out to be 29. That's okay, because you know what happened was in our curve, if I was to bring them near very small region around here, okay, so the gain is 29 here. You see, from the static also you get the same gain, 29.5. okay, from the static response, and from AC response 29.5 roughly. So it's just a matter of, you know, where you are checking it, right? Okay, so now this is clear. Now what I'm going to do is add the phase. Okay, so the phase is doing that. Okay, so the phase is doing this. Now what I want to see is when the gain becomes 0, how much is the phase? Okay, so to start with, the phase is going to be 180 degree, because this is a common source, right? So this is a 180 degree phase, right? So it will roll off to, it will start rolling off. So this is your first corner, and this first corner is because of this CGD over here. That CGD multiplied by AV will be the Miller capacitance referred to the input. That, okay, multiplied by, so that would be the cause of this corner frequency, and there will be a resistance here, right? So okay, am I at the right place? Yeah. So that RC time constant, or the first pole, will come from the Miller capacitance referred to the input. Then over here, so there would be a roll off of 90. So wherever the roll off has taken 90, so this is 180, and this becomes 90 somewhere, right? And before that, this has become plus 90 here, which means that there is a 0 which came in to correct. So there was a fall off at 20 dB per decade, and as soon as you get a 0, you will be 40 dB per decade, and then there will be another corner coming here. So it will give you additional 90. So 90 roll off, flat, or plus 90, right? And then another roll off. Okay, so now what I want to check is the gain becomes 0 here, and what is the phase? Phase is 44 degrees. Now it's around 180 degrees. Okay, now I'm left with 40 degrees. Okay, so my phase margin is 44 degrees. Now I at least need a 45 degrees for a buffer. So don't worry about what I'm talking. Later on it will be clear. Okay, so now why I need a why I'm considering 180 degree roll off? Because if you see this transistor, okay, this transistor has a 180 degree phase shift. And now if you have an additional 180 degree phase shift, then whatever is that voltage, that will cause a feedback to the input which is 360 degrees. This is known as Barkhausen criteria. So what is the Barkhausen criteria? The volt the the phase, wherever the phase rolls off by 360 along a feedback path, okay, the gain has to go below 0, or the gain has to die down 0 dB. So that's basically is the Barkhausen criteria, and at that frequency the amplifier will start oscillating, right? So at that frequency where the roll off has been by 180 degrees, the gain should have decayed to 0. So 44-degree margin is okay, but for feedback circuits it's not. So I want to improve this margin. So to improve this margin, there is one way where I can increase the GM of the device. So when you increase the GM of the device, the Miller capacitance, which is over here, it becomes bigger. AV times of CGD, it becomes bigger, and this causes this pole, first pole, to move in, right, while the second pole is going to move out. So this is called split pole compensation, right? So I'm not going to do, I will go into a separate session on compensation, but here I'm going to do a lead compensation, and that too I can derive it, but for now I'm just going to give you a direct lead compensation here. So I am going to choose here. Now these capacitor values can be tuned. So I'm going to start with 0.5 volt, 0.5 ohm. Sorry, I'm going to start with 50. So this is 0.5 picofarad. So I'm going to start with 0.5. Now there is a way to do lead compensation. You can compute it. Just as I told you, at the start of your career, you are supposed to compute and compute and compute. And once you have an intuition, then you can basically skip that method. But if at a start itself you are going to do a trial and error, so you will become a trial and error engineer. And for example, most of the engineers I see, 99% are trial and error engineers. I don't like trial and error engineers. Okay, so here what I'm doing is a trial and error because I have some intuition. But what it is doing, right, it is introducing a 0 between the first pole and the second pole. So I'm going to do this. I am going to hit here tune. Okay, and I'm going to tune this capacitor, and I'm going to tune this resistor. So let's look at the response. So you see what happened over here? So I am talking about tuning these. Okay, so where is my tuner? Here's my tuner. Okay, so if I was to increase R, okay, so first of all, okay, so what I'm going to do is, so here, so instead of this marker, I'm going to put another marker. So let's put here a delete, and let me delete this marker. And this marker I avoid because I have been telling Agilent to change this marker values. So marker, see what it does. See the gain it is showing in degrees, which is wrong, which is dB, right? So I've been asking Agilent for a long time that please correct this, and they don't want to correct this. So I am on a YouTube platform forcing them to correct this. Okay, so you see here there is the gain of 0, and I have now 65-degree margin. Okay, now 65, and okay, let's pull this point to the left. Okay, so there are different things in this. When you do that, you can cancel the second pole, you can do lots of things here. So 28, 28. So now I have 80-degree margin. Okay. Okay. I don't want to do very large capacitance, but if I want, I can do that. I hate that. And reducing resistor also basically changes your what you call. So I am here. Now I have enough margin. This is minus 90. So this is the 0. So now I have 129 degrees margin over here. This is I have done by doing this, but really I hate losing gain. I'm a selfish guy. I hate losing gain. Because I have lost the bandwidth, right? There's a price to pay here. Marker new. So you see, this is 180. First corner has now gone at 77 kilohertz. Okay, so what is the first corner? This is going to be gain of, sorry, let's put it on the other axis. Marker new over here. So this is a gain of 29. Okay, then gain of 26. This is your first corner, roughly. Okay, and the first corner is occurring at 22 megahertz, right? So I can use this amplifier up to 22 megahertz, right, with a gain of 26 dB. The first corner frequency is around or 19 or 20 megahertz. The first corner frequency is around 20 megahertz. So I can use this gain stage up to 20 megahertz. And then I have put a lead compensation or RC compensation such that I have a margin. I have a phase margin of roughly, let me put here, just 1 second. Okay, I lost the phase margin here. Okay, so it becomes negative here. Okay, I have phase margin of 11.2 degrees, 111.2 degrees. So this is a good gain stage, right? But then there are the drawbacks of, so I can do update schematic close. Yes. So this is a good gain stage, but the problem stays. And what's the problem? The problem is the input voltage range is too little. It's hardly 60 millivolts, 60 millivolts. And then the swing is restricted by the overdrives, right? So these problems can be overcome in other circuits which will come up. Now, so this is a common source amplifier. So I am going to stop here. A common gate and common drain are much easier, which I'll do in the next session. But for this session, I'm going to stop. So I have covered a lot of ground here coming to the frequency response of a circuit. Now, the same thing if I was to do through derivations here, it is going to be very involving, and I will do it because because I'm not doing it for the industry people only. I'm doing this presentation for students also. So I will do a small signal analysis of this amplifier in the next session. Thanks a lot.